Okay, so let us start about the properties of electrostatic force given by Coulomb's law. Okay, properties of properties of electrostatic force given by given by Coulomb's law. Coulomb's law. First property. So although we know the formula, but we have to know when can we use that formula. K q1 q2 by r square, this equation can be used only when the charges are point charges. Okay, so Coulomb's law is valid for point charges. Point charges means suppose these are two charges q1 and q2. Okay, what is meant by point charges? So point charges does not mean that charge is a point, but rather charge is a property which is, which belongs to certain objects. So suppose some object is there and it has got some charge. Now the size of the object may be large, but the distance between them can be very, very large. So suppose if the distance between the charges, which is r, and the size of the object, if size of charged object is very, very small, then the separation then the object, then the charges can be considered as point charges. So this is an important thing. Actually, in reality, point charge does not exist, because point charge means the object is the point. Charge is not the point, the object is the point, because object can be any size, but you consider the object size negligibly small, so that the distance between them is very large. For example, the stars are very far away situated, but they looks like point, because the distance between us and the stars are very large. So then only we can apply the Coulomb's law. Remember, Coulomb's law we can apply only then, but electrostatic force will still exist between, even if the bodies are not point charges. Electrostatic force will exist, but then we cannot use Coulomb's law in those cases where the objects are not point objects. So we need to understand the concept of point object so that we can apply Coulomb's law. Okay, right then, and we know already the formula for that. So formula for that already we know. Let us write second point. Second point is that the forces which is electrostatic force, they are central forces. Electrostatic force is a central force. What is meant by central force? So suppose, for example, this is an object. Two objects are there, and this is the center of the object. The force of interaction acts along the line joining the center. So you join the line, right, and then let us say that they are similar charges, plus q1 and q2. So the force will be acting along this line. Let us say they are going to repel. So forces will be acting along the same line. Okay, that is what is called central force. Okay, next Coulomb's law Coulomb's law, Coulomb's law, not Coulomb's law, you can say the electrostatic force, electrostatic force or field, or field is conservative, conservative in nature, conservative in nature. Conservative means work done by electrostatic force is going to be zero in a circular loop or any loop. So if you take a charge and move in a loop, loop means closed path, and you come to the same point, then the work done is going to be zero. So this we have studied in work power energy in grade 11, conservative forces, right? Then let us go to the next. Electrostatic force, electrostatic force, electrostatic force is valid for all macroscopic scale, but it is valid for microscopic scale, microscopic scale up to 10 to the power minus 10 meter atomic scale, and this idea is a established fact, that means this has already been proven for atomic scale, but in some textbook it is also saying that up to 10 to the power minus 15 meter also, which is the nuclear scale, nuclear size. But if you go distances less than micro 10 to the power minus 15 meter, it is not valid. For distances lesser than 10 to the power minus 15 meter, electrostatic force is ineffective, because of strong nuclear forces, strong nuclear force, because of strong nuclear force. So what happens that when you go for charges kept at very small distance, even smaller than nuclear size, then their electrostatic force will not work. It may act, but it will not be effective, or its effect will not be visible. The reason is that for such a small distances, there is another world of forces, another kind of forces acts, that is nuclear force, and that too strong nuclear force. Okay, all these points are mentioned in NCERT, and very important questions do come from these things. Okay, let us move next. What is point number 5? Point number 5. Okay, so then what else? What other points are there regarding electrostatic? There is an important point. So in electrostatics, we say that similar charges, repel. But I am going to explain a very important case of similar charges can also attract. Let us understand this. Okay. So similar charges, similar charged body, okay, not similar charges. So note this statement, very important. So similar charges mean point charges, point charges. Similar charges means points, point charges, point charges repel, and opposite charges, right? Again here point charges attract. This fact is there, but now if I say that similar charged bodies, similar charged bodies may attract, or repel, okay. Similarly, opposite charged bodies may attract, or repel. Now, how this is possible? How it is possible? Let us try to understand this fact. Suppose if I take bodies. Now, when they say similar charged bodies means charges are present in the body and we don't have to consider as a point charge. We are not taking as a point charge. That means body can be any shape or size. It may be larger and the objects are closer. Okay, like this. Now, let us say that there is sphere and this is the center, and let us say it has positive charge, positive q1, it has positive q2. So positive charges are distributed over the surface of this body. Here also positive charges are distributed over the surface of the body. Now let's understand this fact. So due to charges which are very close to each other, there can be induction effect. Induction means opposite charges is induced in the surface of other object. So due to this positive charge, here there are some negative charges may induce, and due to this negative, of course, positive charges also comes. Similarly, due to this body, here opposite charges may induce minus minus, and here plus plus will come. Okay, so we should note that induction effect can happen for large size body, okay, which are not point objects. Now here what will happen, let's understand this. So this object, now let us take this this object, forces on this object. So here overall charges are positive. So this positively charged body can attract this negative charge here. These negative charges are there. These negative charges will get attracted. Attraction will happen. And these positive charges can repel these positive charges here. Okay, repel this. Repel. Now, these attraction and repulsion which are happening is beside the repulsion of the whole charges. This whole positive and this whole positive, they are repelling, definitely they are repelling. Assuming that they are like point charges, so definitely they are repelling each other. But because of induction effect, you can see opposite charges are developed and it is getting attraction and repulsion. Now, this attraction force is going to be larger than this repulsion force. Why? Because this charge is close to this body and this charge is away from that body. So if the distance is small, force is large. That's how here this attraction is a more attraction is more. This point is important to know. This attraction is more and this repulsion is less. Okay, so because of this, what will happen, that let us say that this body was getting repelled. Okay, this body was getting repelled overall, you know, this whole system was getting repelled. But in addition of that repulsion, now there is a resultant attraction is also there. Resultant attraction is there. resultant attraction is there. So now this repulsion which was happening between the bodies, this repulsion which was happening between the bodies when they were considered as point charges, right? When they were considered as point charges, so they were definitely repelling. But now due to this induction effect, there is a small attractive force, right, on this body. So now what will happen is that instead of happening repulsion, more repulsion, now repulsion will be there, but repulsion will get reduced. This repulsion will happen, but it will get reduced. Similarly, this body is also getting same way. You can also do like that. This body will also get repulsion, but repulsion will get reduced. Are you understanding this fact? Yes. Hmm. So this is a very important concept in NCRT. First question of exercise have been given, but I raised today one objection on this question, that if they say that bodies are similarly charged, but they can repel also, and they can attract also. For example, here these two bodies are repelling. Okay, now repulsion is less if the objects are not point object. But what can happen is, let us say these objects are very close to each other, then this attraction force can become infinity also. And if the attraction force will become infinity, then these objects, instead of repelling, they may start attracting. So that is why I have used the word may. It may attract or it may repel also, right? This is an important fact, right? This may happen. So this criteria we need to understand. But one thing is sure, that repulsion effect will get reduced generally. Repulsion effect will get reduced because the bodies are not the point objects, or bodies are charges are not considered point charges. So this is important concept. Okay, done. Then let us go to the next. So this was point number 5. Point number 6, let us go to point number 6. Electrostatic force. Electrostatic force is a field force. Field force. What is field force? So suppose that point object, let us consider this is a point source. This is called source charge. Source charge. And from this source charge, if you take a point here P at a distance of r. Now, what is the concept of field? So here itself we will develop a basic idea about field and field intensity and the formula for electric field and so on, because we don't have to separately study that. Already in gravitation you have got the idea of field, gravitational field. So similar concept is there. Okay, so what is field, electric field? So suppose there is a charge, and around that charge the space where it can show electric behavior or electric effect, that entire space is called electric field. Okay, so what is electric field? Electric field is the space around a charge, where where it can show electrical effects. Electrical effects means, suppose if I bring a small charge q, or any other charge you bring here or anywhere around this, so that charge will experience force. How this charge, source charge, is applying force on this charge? They are not in contact, but still it is able to apply force through an invisible field. There is an invisible field. So how that field is working? So the force is working like this manner. This charge, source charge, creates a field around it, and any other charge which comes in that field will experience the force of the force due to the field of that charge. So field applies the force. So we have to understand how to measure the field. Okay, field is there, but how to measure the field? To measure the field, let us first try to understand force. So force will be there here. This force will be given as, we already know, k q q by r square. This is the force. Now how stronger is the field there? So how stronger means, if the force is strong, then field will be strong. But force depend on the product of charges, but you want to study the field due to that source charge, so you have to eliminate this small q. So to eliminate this small q, what you can do is, you can divide force by this charge. So if you divide it, it will get eliminated. This is k cube by r square. So this is what is called field. Okay, so field is nothing but force divided by the charge which we are bringing there, right? But here there is an important point to note, that while you are measuring this, and while you are bringing any charge here, that charge we have to consider a small charge. Why? Because if you do not consider that charge as small, then that charge will disturb this source charge, but we want to measure the effect of source charge. So we have to keep this small charge very, very small. So that's why it is called test charge. So this charge is called test charge. And the test charge condition is that test charge must be positive by convention, and test charge must be very small. Okay, so these are the two important conditions on test charge. Test charge must be positive by convention. We are choosing it, and we are choosing it very small. That is why in this formula we have to apply a factor called limit q tends to 0. So when you apply the condition limit q tends to 0, that means the source charge is very small. It will not affect the test charge is very small, and it will not affect the source charge, so that you can measure the field due to the source charge at that point. So source charge, the field due to source charge at a given point will depend only on the source charge properties. That means what is the charge of source charge and the distance of source charge, right, from that point. So this field represents the property of source charge. Electric field. Sometimes this E is called electric field intensity. Electric field intensity, E, represent the property of source charge. Property of source charge. Okay, this is what it is. So it will represent that. So then there will be many things in the electric field, but one important formula is that, because we know that electric field is equal to this F by Q. Now generally it is being defined like that, but instead of now let us say you have measured electric field, okay, you have calculated. Now let us say you bring any other charge at that point, q1, q2, instead of test charge you bring any charge. So how will the force will be acting? So according to this formula, E is equal to F by Q. So F is equal to Q into E. This is how force acts on that point. If you keep any charge at that point, you have to multiply the charge which you are keeping multiplied with the field present there. So whatever field is present there, that field multiply the charge which you are keeping there. That charge may be test charge or it may not be test charge, because now you are interested in calculating the force. Right, now you are not calculating field. So while you are calculating field, then you can write like this limit, but now you are not calculating field, you are calculating force. So this may not be the test charge, it may be any charge, and you have to multiply that charge with the field here. Okay, this is how we will calculate that. Okay, clear? Are you clear about this? Okay, then yeah, So I think these are the important properties, and previously we have also discussed that electric field propagate with the speed of light. So these things we already know that, but still I will briefly discuss here also as one of the property, because in NCERT that is also mentioned separately. Point number 7 you can write. Any change, any change in electric field or electrostatic force takes place very quickly as the electro as the electric field propagates with speed of light if source charge is moved if source charge is moved. Okay, so suppose if this is the source charge, capital Q, and this is a test charge, and let us take that this position is A and this position is B. So right now some force is acting here, some force is acting. Now suppose if you move the source charge from this point to this point, okay, let us say you are moving it, so you have brought to point C this source charge. So you have moved the source charge. It will definitely take some time for the source charge to move. But here the force which was acting due to the field when the charge was here, right, it was acting, and now when the charge is here, due to this force is acting. Now these two forces are going to be different. So when this charge was here, force was along this line. If you want, you can calculate that. Let us say they are positive charge, so force was in this direction. Let us say F1. When this has moved here, the force may go here in this direction F2, because distances also changes, direction of the force also changes. So this change will happen instantaneously, very small time it will take, and the change will happen very fast with the speed of light. Why? Because when charges goes from here to here, its field changes, right? Its field, and the change of that field or the field propagates in the space with the speed of light. That's the important concept, but this will be discussed in electromagnetic waves chapter. Okay, so right now we can just understand up to this much. Okay, right. Then I think these are some of the important things, and for electric field lines, now we have to discuss about electric field lines. Okay, let us discuss about electric field lines. Electric field lines. So suppose if you take a positive charge, so let us write some properties of the field line. And what is field line? First of all, let us write the definition of field line. So what happens that if you consider a positive source charge, now if you keep a test charge here or here or here or here or anywhere, so if you keep it here, then it will experience force, because this test charge is anyway positive, so it will move away. If you keep the test charge here, it will move away. If you keep it here, it will move away. Here also if you keep, it will move away. Here also if you keep, it will move away. So you can see that it will move radially away from this body. Okay, so the test charge anywhere you keep, it will move away. But if you keep near, then the force will be strong, or field will be strong. If you keep near, so field will be strong. So if I take nearby point, then more field will be there. right? And if I keep away, the field will be less. So field is going radially away from this point, from the source charge, but the strength of the field decreases, because if you go near, force is more, field is more, and if you go away, force is less, field is less. Okay, so you can say that you can try to join a line like this line you can join. Okay, try to join like a radially outward, so many lines you can make, arrow you can give. Okay, you can draw like this, so many lines you can draw like this. Okay, so these lines which are there, these lines are nothing but it is the direction in which the test charge will move. A positive test charge is moving. Suppose you keep here, it will go away, but only thing is that the value will be different, field will be different, or force will be different. So this field is not a uniform field, it is non-uniform, non-uniform, non-uniform field. Okay, and it is going radially outward, radially outward, radially outward. Similarly, if I choose a negative charge, the reverse effect will happen. If I choose negative charge, then if you are keeping the test charge here, then it will get attracted, right? The test charge will get attracted. If I keep here, it will get attracted. If I keep here, it will get attracted. If I keep here, it will get attracted. And if I move little bit away, let us say if I keep little bit farther, so here it will also get attracted, but less. So here force will be more. When you consider nearby points, force will be more, right? Force will be more means I am representing it by thick lines, and if you go further away, force will be less. So thin lines can be used to represent that. Okay, like this, and so many things. And you can also join them with like a straight line to indicate this field. So you can join using a straight line, but you should note that the field lines is thickness is not the same. Thickness represents the value of the field. So nearby line will become thicker, and away here line will become thinner. Here also same thing. Nearby this it is thicker, away when you go, because it is representing non-uniform field. Okay, and another thing is that in this case, due to negative charge, it is radially inward. So here also it is non-uniform, non-uniform field, and in case of negative charge it is radially inward, radially inward. Okay, so like this we can understand. This is about the field due to what? Due to point charge. This is about the field due to point charges, and that also isolated point charge or single point charge. Okay, so we can understand about this field, electric field lines. Okay, right, then let us move to next. So some properties of field lines we can try to write. What are some of the properties of field lines? So let us write some properties. Properties of field lines, electric field lines. First property, we can see that for isolated charges, for a single isolated point charge, field lines either start at infinity or end at infinity. So for example, let us say that we have discussed about positive charge. So if you take a positive charge, so field due to positive charge is going radially outward, radially outward. So field is coming out from the positive charge, it is starting from the positive charge, and it is going where? It is going to infinity. So here the field line for a positive charge, it is starting from that charge, it is going to infinity. But if you take negative charge, then field due to this negative charge is starting at infinity and it is reaching to this charge like this. Of course, it is a non-uniform, though that point already we mentioned, but we are now drawing like this. Okay, so field is here, field is starting at infinity. Okay, you can see that this field is starting at infinity, and in this case you can say that field is ending at infinity, ending at infinity. So now we can write one thing, that electric field will start from point charges and end at point negative charges. Okay, so electric field lines start from positive charge and end at negative charge. What does that mean? Now you can say that here, if you take this negative charge, so field is coming from infinity, so that means at infinity you can assume that there will be some positive charge, because field starts from positive charge. Similarly here, field is going to end at infinity, so that means at infinity there must be some negative charge. You have to assume that. Okay, so this is the important point. Next, point number 2. Field strength will be more if the lines are closer, and field strength will be less if lines are separated further. What does that mean? Suppose, for example, if you see electric field lines going like this. Suppose you are seeing electric field lines going like this. Now you see here at some point here, if you see, the field lines are very close to each other, right? All the three lines. Here the field lines are further away from each other. So if I take point A here and point B here, so at point B the field lines are very close, so there the electric field strength or electric field intensity will be more. So field is higher at, suppose I write field as B, so field at B is more than field at A. Okay, this is a simple rule, and more about this we will be discussing when we will discuss electric flux. Okay, let us move next. Point number 3. Electric field lines due to charges, due to electric charges do not form closed loops. Okay, they will not form closed loops. So electric field lines coming from the charges, but there are some electric field lines which can form closed loop. Okay, that electric field is not produced due to charges, they are produced due to changing magnetic field. Okay, note here, electric field lines produced due to changing changing magnetic field form closed loops. Okay, let us go to the next point. Number 4, electric field is conservative in nature. Already we discussed that in forces, but here also this point comes. But again, here this electric field is which electric field? Electric field produced by charges. Produced by charges. What about another point as I told? So, electric field produced by varying magnetic field. Varying magnetic field. Electric field produced by varying magnetic field is non-conservative. Is non-conservative in nature. Okay. More about that we will be studying electromagnetic induction EMI. Okay, so I think these are the important properties of one more property I'm missing. Okay, that also let's write. Electric field lines do not cut each other. Electric field lines do not cut each other. Okay, why? Why? Because where electric field lines will cut, there the direction of test charge will not be a unique direction. Let us say that if electric field lines are cutting at this point, suppose electric field lines is going like this and another field line is going like this. Now if you keep a charge at this point here, suppose you keep a test charge here, so due to this field line, force will be in this direction force F1, and due to this force will be in this direction. So this charge cannot move in two different direction. This charge cannot move in two different direction at this place. It has to move only one. It has to move only one direction. So you cannot represent. See, the idea is that you cannot represent field lines, because whenever you are representing field lines, you are representing the resultant field line, not that you are representing separate field and then you are doing calculation and then you are drawing the resultant. No, whenever you are representing, you are representing the resultant field lines. That means how to get that field line? You are putting the charge, test charge, and the direction in which test charge is moving, those lines, okay, that line in which the test charge move, that is what is the field line. But if field lines cut, then how it will move? So in that case, you can draw the vectors and you can try to theoretically calculate. Theoretical calculation is different, but practically when you keep it, it cannot have two direction. Okay, because two directions at the point of intersection, of field lines is not possible. It will have a unique direction. So instead of that, you can show a resultant field like this. Okay, if you show a resultant field, then you may not show these two field lines, because let us say this field line is representing the resultant field. So then there is no possibility of intersection. Okay, so this is important point to note. And one last point, point number 6, electric field lines form closed, form continuous loop. Electric field lines form continuous loop without without break for isolated charge. Okay, so for isolated charge like point charge, positive or negative, field is going radially outward or radially inward. So there is no break in the field. Everywhere field is there without any break. But if there are more than one charge, let us say there are two charge, three charge, then due to those charges, there can be resultant field at any point, and sometimes the resultant can be zero also. And if the resultant is zero, then there is no field there. There is no field there. That is called, break or discontinuity. So discontinuity can happen, but it can happen only when there are more than one charges. Okay, and there where the field is zero, that is called null point. Okay, so those things also we will be seeing in the problem. So these are all the important ideas about that. Okay, important idea about the field and electrostatic forces. I think we have covered a good amount of this concept. Now problems are important to solve, so I think we can start working out problems. Okay, so what we can do is you can take up questions of electrostatic force and electrostatic field. These two things we can work out questions. Okay, let us take some questions. Let us start with some problems. Worksheet 1, let us start worksheet 1. Let's start with question number 1. An electroscope is having two identical gold leaves. What is electroscope? Electroscope is a device to detect charges on a body. Okay. So it is given a positive charge causing its two leaves to separate. When an object is brought near the metal disc at the top of the electroscope, the separation increases even further, we can conclude. So this is called electroscope. The diagram is given here. This is a rough sketch, and these two are called foils. They are gold plates. So there are two gold plates, and any charged object you have to touch here. This is like a metal part, metal. So any charged object you touch with this metal, the charge will transfer to this metal and it will go to these two plates. And if they have charges, both these plates will get same charge and they will get separated. Some angle will form between them. So that means it is charged. But suppose there is a uncharged body. If you touch it, nothing will happen to this, right? And let us say it is already in this position, and if you bring a opposite charge, then it will contract. Okay, so things may change according to what type of charges you are bringing here. So now what is the question here? An object is brought near the metal disc at the top of the electroscope, the separation increases even further. Okay, so first it is given a positive charge causing two leaves to separate. First positive charge already was there, it was already separated. Now they are saying when an object is brought near the near the metal disk. Note that an object is brought near the metal, it is not touched. That means induction, you have to think about it. Okay, so already it has some charges right now. It has already some charges are there, plus, 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 plus. They have already said that it has some positive charges, right? Now they are saying that you are bringing some body and it is further expanding. So that means what? That means here you are bringing some, let us say some rod you bring here, but you are not touching it. Okay. So if you are bringing a rod but you are not touching it and it is further expanding, means here positive charges are developed. So due to this rod here, more positive charges are getting developed, right? So it is further expanding more, it is expanding like this. So if it is happening, means positive charges are developing here. Why? Because of induction. That means here negative charges must develop, negative charges must develop, and here negative charge must be developing because this rod must be positive. This is how reverse way you can think. So this is positive rod, this is going to induce negative charges, and here positive charges will be developed, right? So I think the question is, what is question, options, let us see, that the object is positively charged. Yes, object is positively charged. This is the object. This object is positively charged. Okay. That the object is electrically neutral. Is it possible that it can be neutral? No, because all the charges are here only. So neutral body, it will not induce any charges, right? Correct. The object is negatively charged. That is not correct. Only that the object is charged. Suppose if you put this negative charge, then positive will come, and here negative will come, it will contract. So that is not possible. Okay. Let us go to the next question. So correct option will be option A, right? Let us move to the next question. Question number 2. 2-point charges plus 9e and plus e are kept 16 centimeter apart. Where should a third charge be placed so that it is in equilibrium? Okay, so there is a charge of plus 9e and there is a charge of plus e. Okay, let us say this is the line joining these two charges and they are similar charges. So where should we keep a charge, any other charge q, so that that small q should be in equilibrium? So if you take for example here somewhere, but definitely in between you need to keep. So in between you need to keep. And where should you keep? Definitely you should not keep near to, because this charge is larger, you have to keep near to this. Let us say this distance and this distance, you have to assume something. Have the given total distance? Yes, total is 16 centimeter. So let us say from here this is x, then this will be 16 minus x. Remember this is in centimeter. Okay. Now let us try to calculate. So here it is in equilibrium, means what? Here equilibrium means force due to this one and force due to this one, both the forces must cancel out. Okay, both the forces will cancel out. So let us say that this force due to B is F1 or FB, due to A it is FA. So both FA and FB must be equal, then only they will cancel out. Let us now write the forces. FA means due to A. So K, Q1, Q2, Q1, Q2. So this is Q and this Q is E, right, by x square, and force due to FA is what? This is FA. I think this is FB I have written. This is FB. Okay, we have to equate. Then FA you write. FA will be what? No, this is FA only. FB you write. FB will be what? K into 9e into q divided by distance is 16 minus x whole square. Okay, let's write this and now try to find out what is x. Solve it. Okay, so kq will get cancelled. kq e also get cancelled. So 16 minus x by x whole square becomes equal to 9. Just solve it very fast. So 16 minus x by x is equal to 3. Then what? 16 by x minus 1, so plus 4. 4 into 4, x become equal to 4. Clear? Right. So x will be 4 and they are giving the options like how much distance from plus 9e and e. So from here it is 4. So from here 16 minus 4 means 12. So 12 centimeter from A and 4 centimeter from B. So 12 centimeter from A, that means plus 9e. So you will get the correct answer as option B, right? Okay. Then so like that you need to work out now problems on this topic. Okay, and worksheet have been already shared, so let us start working out questions on this, and meanwhile gradually we will try to cover all the important topics. Okay, right. Okay, fine, then we will see in the next class. Okay, so please work out NCRT questions as well as this worksheet, then we'll see next class. Bye bye. Thank you.